Hello everyone, my name is Alexos Zeakis, and today I will be presenting token join, efficient filtering for set similarity join with maximum weighted bipartite matching. This is a work done in collaboration with Dimitrios Koutas, Dimitris Zacharidis, Odysseas Papapetru, and Vanalos Koubarakis. This is the outline of our presentation. We're going to start with an introduction defining the problem, then move on to the state of the art. Then we're going to present our approach, and then we're going to present the experiments and the evaluation of our methods, and finally our conclusions. The set similarity join problem is a widely studied problem with many applications, such as data discovery, data cleaning, and data integration. For example, you might want to detect similar social media posts or news headlines. In the traditional definition of the problem, we are given as input a collection of sets, denoted as D, a similarity function like Jacquard, and a similarity threshold delta. Then, the output includes all pairs of sets that their similarity exceeds delta. A limitation of this definition is that only elements that match exactly can contribute to the similarity score. In our work, we study a variation of set similarity join, which overcomes this limitation. Each set R in collection D comprises still a set of elements, but now we want the elements to not match exactly, but approximately. This means that instead of 0 or 1, the elements can have any score in between. This is done by a specified function phi. In case we use Jacquard similarity as phi, then each element comprises a set of tokens, and the similarity is computed by their intersection over their union of tokens. In case we use normalized edit similarity as phi, then we use the edit distance to find the difference between the two elements, which is normalized by the size of the maximum element and subtracted from 1 to represent similarity. Let us now define a new set similarity function that takes into consideration all element similarities computed by phi. First of all, we construct a bipartite graph with R and S as partitions, where the nodes are the elements and the edges are weighted by the corresponding element similarities. We compute the maximum weighted bipartite matching score, which is then normalized by the size of the sets to produce the final set similarity score. Note that if we did not use a similarity function phi and allowed only exact matching between elements, then this scoring function would be similar to Jacquard. Our problem now is that given a similarity threshold delta and a function phi, we want to return all pairs of sets in collection D that their similarity score with regard to phi exceeds delta. Let us now consider an example. Assume two sets R and S, each having 3 elements. We can see that only R3 and S3 are identical, while the other two pairs are similar. Using the traditional definition for set similarity join, we would calculate a very low similarity score of 0.2. Instead, using the definition that relies on the bipartite matching, we obtain a bipartite graph with 9 edges, where R3 and S3 have a similarity of 1, and R1 and R2, R1S1 and R2S2 match approximately with a similarity score of 0.5. This produces a matching score of 2.5 and consequently a set similarity score of 0.71, which is significantly higher than 0.2. Now let's move on to the state of the art. The challenge in this problem is the high computational cost. As in the traditional set similarity join, a naive approach would examine all possible pairs of sets. This has quadratic complexity and therefore it does not scale to large collections. Even worse, in our case, the verification cost is also very high due to the complexity of computing the maximum weighted bipartite matching. Typically, methods for set similarity join follow the filter and verification framework. For each set R in the collection D, first, a subset of the tokens called prefix or signature is selected and used to generate initial candidates. Then, one or more filters are applied to refine the set of candidates. Finally, all surviving candidates are verified to find the true matches. The goal is to define filters that are both lightweight and effective. The state-of-the-art method for our problem is Silkmoth. It also uses the filter and verification framework. For candidate generation, it considers all unique tokens of a set R, denoted by TR, to construct a signature. This signature, denoted by KTR, is a subset of TR, such that if no token in it is contained in any another set S, then the similarity score of R and S cannot exceed delta. Silkmoth introduces two filters, namely check filter and nearest neighbor filter. The first checks if a candidate S has at least one element similarity RS that exceeds a personalized threshold delta R for this element R. These personalized element thresholds are constructed based on the signature KTR. NNF avoids computing the maximum weighted bipartite matching by assigning each element R of R to its nearest neighbor in S. This allows collisions and thus is not a valid matching, but it constitutes an upper bound of the final matching. Now let's move on to our approach. The key difference between Silkmoth and our approach is the following. Silkmoth uses only a few tokens of R and the filtering is element-based. Instead, our approach, called token join, performs token-based filtering and uses all tokens of R. As shown in the experiments, our filters are both more lightweight and effective, making our method around an order of magnitude faster. Now, the central concept in our approach is the notion of token utility. The token utility represents a contribution of a given token T in element similarities and also in set similarities. Thus, we introduce the utility UT. It is defined in such a way that by adding the utilities of the common tokens, we can derive an upper bound for either element or set similarities. As an element level utility, the utility of token T in an element R is 1 over the size of R. For example, if we have an element with 4 tokens and then a candidate misses 1 token, we can assume that even if it matches all 3 tokens, then the element similarity cannot be over 0.75. In other words, by missing 1 out of 4 tokens, the candidate's matching score reduces by 1/4. This also extends to set level, where now each token sums all element level utilities of the element it belongs to. Finally, the key property here is that the final matching is bound by the summary of the set level utilities of the common tokens. For all tokens that the candidate S has missed, it has lost the corresponding utilities and the matching of R and S is now bound. Now let us present our algorithm. We have first some notation where we transform the threshold delta into two matching thresholds, theta R and theta RS. For each set R in D, first we initialize the remaining utility sigma to the size of R. That translates to all elements R having element similarity 1. While examining tokens, this remaining utility is decreased by the corresponding set level token utility. Then, for each token T in TR, we examine candidates S. If the remaining utility is enough, meaning over theta R, then we generate new candidates and initialize their collected utility to 0. Otherwise, we only update the existing candidates. If a candidate S contains a token T, then S is rewarded by the set level token utility of T. Once the collected utility plus the remaining utility drops below theta RS, we can prune S. Finally, for all remaining candidates, we apply the nearest neighbor filter and verification. This algorithm is very lightweight but has limited effectiveness. Thus, we introduce two more filters. Recall that the candidate S is pruned if the collected utility and the remaining utility are below theta RS. The positional filter tightens the remaining utility by using the remaining utility of both R and S instead of only R. This requires that tokens in all sets are sorted according to a global ordering. Furthermore, the joint filter tightens the collected utility by considering a combination of the utilities provided by both sets. This relies on a more elaborate definition of token utility called joint token utility. Here we summarize the three variations of our methods. The basic algorithm called TJ computes the collected and remaining utilities only based on TAR. TJP extends TJ by applying also the positional filter, which computes the remaining utilities based on both R and S. Finally, TJPJ extends TJP by adding the joint filter, which computes collected utilities jointly for R and S. Let us now present an example. Assume two sets R and S with 3 elements each. Their matching score is 1.8 and their normalized similarity is 0.43. Assuming a threshold of delta 0.75, let us check now how the different filters perform. First, we see the token utilities of both R and S along with their remaining utility sigma. The tokens that show utilities with brackets are tokens that are included in more than one element, and inside the brackets we see the accumulated utilities necessary for the join filter. The common tokens are shown in blue. First, we examine TJ. For their common tokens, S collects the utility of R and utilizes sigma R to check the condition. We notice that the total upper bound is 3 until the last token where it drops to 2.75. When we examine TJP, the first row stays the same since we still use the utilities of R. The change comes in the second row where we take the minimum of the two remaining utilities. Thus, we observe that now the upper bound drops to 2.75 at T5, but S is still not pruned. Finally, in DJPJ, we examine both utilities of R and S, thus we also change the first row. Consider T7, for example, where R has T7 within two elements, while S only once. Thus, the joint utility in this case is 0.25. The same holds for T5. Hence, the total upper bound drops to 2.5 at T7, and S can be rejected since theta is 2.57. Selecting an appropriate value for the similarity threshold delta is not straightforward and may lead to too many or too few results. To overcome this, we also introduce a variant of our method that can solve the top K version of the problem, which returns the K most similar pairs. It works as follows. First, we initialize the threshold delta to bootstrap the candidate generation stage. Then, for each set R that we're examining, first we generate candidates based on the current delta, and then we maintain a priority queue for all candidates based on their upper bounds. For each candidate we extract, we check its status to proceed to the next stage. The stages are positional filtering, join filtering, NNF, and verification. After each verification, we also update delta accordingly. Now let's move to our evaluation. In our experiments, we used 6 real-world datasets. We can categorize them in 3 categories. 2 have small sets, 3 have medium sets, and 1 N1 has large sets. The algorithms that we compare in the threshold experiments are SilkMoth, TJ, TJP, and TJPJ as defined previously. The algorithms that we compare in the top K experiments are TokenJoy K, an adaptation of SilkMoth to solve the top K problem, an adaptation of a top K join algorithm for traditional sets in order to work for sets with bipartite matching, and finally an oracle method that takes the final threshold of each setting and executes token join with this. We examine the execution time and the pruning effectiveness of the different filters. In the first experiment, we vary the similarity threshold delta from 0.95 to 0.6. Token join clearly outperforms SilkMoth in all cases. SilkMoth has failed to terminate in some settings within a 5-hour window, such as an G delt for delta 0.65. TJPJ is usually close to TJ and TJP, but it's clearly faster in N1, where we are dealing with very large sets, and therefore the verification time of the remaining candidates is higher. In the second set of experiments, we vary the data size D from 20% to 100%, and the threshold here is 0.8. The observations are similar with the previous experiments, where token join is clearly better than SilkMoth, and the major differences between TJPJ and TJ or TJP lie in N1. As a summary, TJPJ is 9 times faster than SilkMoth on average and up to 37 times faster. Regarding TJ and TJP, TJPJ is 1.65 and 1.57 times faster on average and up to 10 times faster. And finally, in an indicative example with N1 and delta 0.8, we can see the effectiveness of our filters. SilkMoth leads 6 billion pairs to NNF, out of which 3.63 million are true pairs. Instead, in our methods, this number is 5 millions for TJ, 4.8 millions for TJP, and 4 millions for TJPJ. The difference is huge, justifying the differences in execution time that we observed in the previous slides. Finally, in the top K experiments, we vary the value of K. All methods had the same delta initialization, and we noticed that TJK is 6 times faster than SMK and FJK on average, and up to 25 times faster. In DBLP and mine, TJK is close to the time of the oracle, which indicates that the initialization of delta and the candidate prioritization are highly effective. Finally, summarizing contributions. First, we addressed the problems of set similarity join based on maximum weighted bipartite matching. We introduced a new approach that relies on token-based filters rather than element-based ones. We have also proposed a novel algorithm for token join, which outperforms the baseline methods. Finally, we conducted experiments that show our proposed filters are both more lightweight and effective compared to previous work. And regarding the future, we're examining ways to make our algorithms work in parallel and in distributed environments, as we also want to design approximate algorithms to deal with very low similarity thresholds. Thank you for your attention.